Hey, what's up? It's Hutch here, and we're on 9-6, Module 9, Lesson 6. This is your last lesson in the module, and it's on simulating chance events. So basically, when you have some sort of theoretical probability of what could happen, sometimes you want to play it out and see how that theoretical probability would play out in an actual experimental situation, but you can't necessarily carry it out in real life, so you have to run a simulation. And so I'll sort of explain what I mean by that, or you'll understand as we continue here. So for example, let's say that a cereal company places a prize in 1 out of every 3 of its cereal boxes. Obviously, you can understand the theoretical probability is 1 out of 3, but you're not going to go buy 100 cereal boxes to see if that actually is true. Okay, so instead, what you would do is use a spinner or some sort of computerized simulator to carry out that simulation to see the results. Okay, and so you can see, since it's a 1 out of 3 chance of having a prize, you do a spinner that has 3 sections, one of them being like the good, it has a prize section. Okay. So another question though, let's say you don't have a spinner and all you have is a 6-sided number cube. How could you use that 6-sided number cube to still run a simulation on this event? Okay, so think about it. A number cube has 6, it doesn't have 3. So what could you do? Pause, think about that, and then we can write something down. All right, so if you think about a number cube, it's split up into 1, 2, 3, 4, 5, 6. You know that the probability of having a prize is a 1 out of 3. So instead, we could just make a proportion, right? And think about it, well, if there were 6 sections, what would the numerator be? Obviously, times 2 over 2. 2 out of the 6 sections would have to count as a expected or desired outcome. So all we could say is something like, well, if I roll a 1 or a 2, then that counts as a successful outcome. And then 3, 4, 5, 6 counts as a negative outcome, meaning the cereal box doesn't have a prize. And so that's how you could be creative with something like that. So let's take a look. We have 2 different kinds of simulators: a spinner with 4 equal size sections, or a coin. Okay, so we know a coin is used for sort of 50% chance scenarios, and then a 4 equal size sections gives us a little bit more flexibility. So let's take a look and see what simulation you would use. Okay, and it says place an X in the column for the correct simulator. So your favorite book out of 4 books is randomly assigned. Obviously, if it's out of 4 books, we would use a 4 equal size section spinner. Favorite baseball team has a 3/4 probability, obviously a 4 equal size section. A 1 out of 2 chance girls win the first game. Obviously, a coin would work well for that, 1 out of 2. 50% chance of rain, coin would be perfect. And a marble chosen from a bag containing 4 different colored marbles. Obviously, a 4-section spinner would work to simulate that event. Okay. All right, let's go ahead and take a look at 2 other examples just to continue to get you some familiarity with this. So when you design a simulation, you just need to determine what each outcome represents and choose, okay, what counts as a success, what counts as a failure, and then choose something to carry out that event. So coins, number cubes, or spinners are often used. Okay, so you can see if we're dealing with a weather type event, okay, it rains 50% of the days. What's the chance it'll rain 2 days in a row? We could use a coin to represent rain or not rain, and then go ahead and flip to carry out that experiment. We could also use a 4-section spinner or even a 2-section spinner, just making sure that rain is 50% and no rain is the other 50%. Okay, same with football. If a professional kicker makes 2 out of 3 of the field goals from 40-yard line, what's the probability that he makes 2 field goals in a row? We could just spin the spinner twice and document our outcomes. Okay, we just need 2 out of the 3 being the success and 1 out of 3 being the bad. We could also assign 4 of the numbers to a number cube, because remember, if it's a 2 out of 3 chance of success, we could just set it equal to 6 instead for a 6-sided die, and times 2. So 4 out of the 6 numbers would count as success, and 2 of them would be not successful. Okay, so that's an option for you there. So let's go ahead and try it out here. We have that original scenario, but with the cereal boxes. But in this one, the probability of a box containing a prize is 1/3. And they want you to design and simulate an event that estimates the probability of randomly selecting a 2-pack that contains a prize in both boxes. And they want us to run this simulation 10 times. Okay, so I don't have a spinner handy, so we could go onto Google and find a free spinner and things like that, which is what we're going to do. So I went ahead and already did my spinning, but I would encourage you to go on. I want you to click this online wheel link, open Safari, and it's going to open up this Google spinner. Up in the top left where it says wheel size, you're going to want to click that and change it to a, come on, where's the numbers? Let me just refresh this here. Change it to a 3-number spinner. And so obviously we can have number 1 be a success and then 2 and 3 be not successful. So let's go ahead and bring up Notability, and I'll just walk you through what I mean by that. Okay, so we have our spinner, okay, and here's our data. So pack 1 means that we have a 2-pack. Okay, so this is a 2-pack. And so basically you're going to spin to simulate opening up one of the boxes. And so since it's on a 2 and 3, that's where I put in an N for box 1. And then I'm going to spin as a simulation of opening box 2. And for mine, it actually landed on a 1, so that's why I put a Y. Okay, now, did both boxes have prizes in them? No, so I just put a line. So that was unsuccessful to both boxes having a prize. So go ahead and run the simulation, continually tapping spin and see what it lands on. Putting an N if it's on a 2 or a 3, and a Y if it opens or if it lands on a 1. Okay, so you can run through that simulation, go ahead and pause and see what your data plays out, and then we can go through this together. All right, so obviously I finished mine, and I only had a yes in 2 spots 1 time, okay? And so the chance of me having both boxes have a prize was only 1 out of 10 for me, but you can write what yours is. Okay, so how many packs have had prizes in both boxes? Only 1 2-pack. So what is the probability? Well, that's a 1 out of 10 chance, which you know 1/10 is 0.1, and swoop, swoop, we have a 10% chance of that happening. Okay, so the estimated probability based on 10 simulated trials of a 2-pack containing prizes in both is only 10%. So let's go ahead and take a look at the theoretical probability of that happening. So remember, we learned the probability formula for simple events, okay, that are independent of each other. And so all you do is you say, well, it was a 1/3 chance of getting a prize in the first one. Okay, so the probability of event A times the probability of event B. And the probability of getting a prize was 1/3 in the second one. And so that ends up being 1/9, or let's go ahead and pull up our calculator. As a decimal, 1/9 is 0.1 repeating. And then swoop, swoop, we're at 11.1 repeating percent is the theoretical probability. Okay, so really, I mean, 11.1 repeating compared to 10%, they're actually pretty close between theoretical and experimental. And so that's how you could carry out a simulation without buying tons of cereal. All right, example 2, let's go ahead and interpret simulations of compound events. Okay, It says a computer simulation was designed to simulate rolling a number cube multiple times until all the possible even numbers were rolled. So we're just rolling until we rolled 2, 4, and 6. This relative frequency bar graph, and remember that means they're already giving the percent, shows the number of rolls needed for the computer to roll all of the even numbers. Okay. So these here on the left side, remember, are the percent, or sort of that experimental probability, written as relative frequency, which is the same thing. Find the sum of the relative frequencies that indicate that 6, 7, or 8 rolls were needed. So we're only looking at 6 rolls, 7 rolls, or 8 rolls were needed to obtain all the events. Okay, so we're adding those probabilities up. Okay, and it's a little hard to see, but you can see this one's 0.8, and we can see it down here too. We have 0.20 and 0.12, okay? Or 80%, 20%, and swoop, swoop, 12%, okay? All right. Oops, sorry, that's 0.08. I was going to say that's not 80%. 0.08. There we go. All right. So let's go ahead and we can see that we're adding those up. They add up to 40%. And so the relative frequency ratio is 40%, which we know is the same thing as the experimental probability. Okay. So based on this experiment, okay, it takes 8 or fewer rolls to obtain all of the even numbers on the number cube. That probability is 40%. Okay. So sometimes they're just going to ask you questions. You have to understand how to interpret them. So let's go ahead and try this one. It says Jake designs and conducts a computer simulation with 20 trials. Okay. You can't tell that from looking at this. Okay. There's nothing that says how many trials on here, so you only know from up here. They use the data from the simulation to create the relative frequency bar graph shown below. It shows the relative frequency of the number of spins needed for a 4-section spinner labeled 1 through 4 to land on every single number at least once. Okay. Using the graph, what is the experimental probability? So here's the information that more than 7 spins are needed. Okay. So more than 7 is 8, 9, 10, and 11. Okay, so what's the probability that you need more than 7 spins? They already have given the probabilities, so we just need to add up those probabilities. So go ahead and pause and try that out, and then you can see what the results are. All right, so step 1 is writing down the probabilities. You can also write it as a percent if you'd prefer. So swoop, swoop, we have 5%. We have swoop, swoop, 10%. And we have 0%, which doesn't really matter any. And then we have 15% here. And all we have to do is add those up. So the probability of, let's use inequality symbols, greater than 7 spins needed equals, so we have 10, 15, 15, 15 is 30%. We're just adding up all those numbers, okay? All right, so there we go with that one. And guess what? That's it. So let's head to the practice and homework and take a look at what we have here. So number 1, it says, suppose the chance of rain on Saturday is 2/5. So rain is 2/5. And the chance of rain on Sunday is also 2/5. A student wants to run a simulation to estimate the probability that it'll rain on both days. How can the student model the chance of it raining on each day? Design a simulation. Okay, so we, of course, can calculate that by doing 2/5 times 2/5. Okay, probability of the one happening plus the probability of the other. Okay, but they're asking us to model the chance of it raining each day through a simulation. So we just have to think, well, what could we do? We can't really do a die number cube because it's out of 5, and we can't turn that denominator to a 6. So we're going to have to do something like a spinner. okay, to run that simulation, okay, and make it out of fifths, okay. So maybe we would do something like draw this. To make fifths is sort of hard. I'd do a point here, and let's see. There's no like beautiful way of making fifths on a spinner. Maybe you'd even go to Google and see what fifths look like. So let's go back to our Safari here and see what that would look like here. So we can change it to 5 numbers. Okay, let's stop it there. Okay, maybe even what would work well for something like this is go ahead and screenshot this. See, we're being creative here. And we can actually hit done on this, save to photos, make you go bye-bye, go to our gallery, grab our spinner. Where is my gallery? Come on, gallery. I don't want stickers. I want actual gallery. Why is it only on stickers? Oh, there we go. Sorry. All right, this and done. Okay, so we'll take that. And technically, I guess you wouldn't have to have a picture. It says, asks you how. So we can say use a 5 equal sized section spinner. Okay. Number 1 and 2 are good. Okay, and instead of good, we should probably say our rain 3 through 5 are no rain. So that would be designing a simulation, okay? So part B, suppose the table shows the results of 10 trials of a simulation. And I will say this too, on your test, you're going to have to draw the spinner that would fit the simulation, but it won't be out of 5 because that would be cruel. Suppose the table shows the results of 10 trials of a simulation, and R represents rain, N is no rain. According to the results, what is the experimental probability of having rain on both days? So remember, I would go through and highlight when there was rain on both days, okay, and then calculate the experimental probability. So that's something you can do on your own, but remember when it asks you for probability, you actually want to, what is this thing? Go away, whatever you are. Oh my gosh, chaos. I can't see it now. That's okay. Maybe if I hit undo, it'll go away. No, it's like a glitch, figures. Okay. So remember when you do that, you need to write what is the probability of rain both days and then equals. Okay. All right. Let's take a look at the next one. Okay. Number 2 is an open response, and this is the last one here. Lee designs and conducts a computer simulation with 30 trials and uses the data from the simulation to create the relative frequency bar graph. So remember, all that data is the percentage. It already is the experimental probability, okay, written as relative frequency. The graph shows the relative frequency of the number of spins needed for a spinner divided by into 6 equal sections labeled A through F to land on each letter at least once. So using this graph, what is the experimental probability that more than 10 spins are needed to land on each letter? Okay, write the probability as a percent. And remember, you need to write probability of the event equals and write it as a percent. And this is where you put in the event. And you're going to have to do this for the test too. So be aware of that. Okay. All right, go ahead and work on that and let me know if you have any questions.